this is really extraordinary, but that's what you have to have in order to manufacture in space, is something that operates and looks like that. That gives you enough power, that gives you the environment to do it in, that gives you powered up rack spaces to bring things up in. So let's talk about what it is that's up there that they ended up finding out after spending $4 billion on experiments that was put through all the universities. $4 billion got you a whole lot of knowledge of what it's like to manufacture things in microgravity. And microgravity is a really unique environment. You can't do it here on Earth. There's no way you can do it. Is that when you're talking about making things on Earth that are down at the atomic level, and this gets into the nano discussion, when you're talking about that, it tends to, with the weak, the strong magnetic, and the gravitational forces that we experience here on Earth, you tend to have things clump up. There's other more scientific words for that, but it's clumping up is what happens. And if you want to make things equally distributed for whatever reason, you need to send it up to space. Now, there's been some artificial ways to do that. You can go up and you can do the vomit comet, but that's only sustained for just a little bit. You can also put it into a sounding rocket, which is a little bit more. But in most of these instances, you need to grow biological cultures, crystals, things like that for a long time. Crystals actually take from 6 weeks to 3 months to grow. So when you start looking at, what are you going to do and utilize it for? Why are we sending all these COTS rockets up? What's the point of all this? And is there going to be a demand on the other side? That's where I come in. Is when we looked at SpaceHab, I said 22 years we've been sending this stuff up. It's not easy to send things up to the International Space Station. If you're going to send up a piece of metal up there that's oxidizing, you need to know if there's another piece of metal up there that's also oxidizing that creates a poisonous gas that gets into the air handling system and kills somebody. Well, NASA just doesn't let anybody just show up and say, hey, I want to be sending some stuff up to space. You have to have a huge amount of knowledge to have the manifest and the ability to go through the safety review boards, all the necessary pieces. And we have 60 engineers that's all they do. Out of 200 people, we have 60 that's all they do is qualify assets to space. So that's a big deal, and it should be, because otherwise one guy that dies up there, and as we've seen with the other space shuttle mishaps, that is not politically at all correct. It's not acceptable. So they're very, very careful about what goes up there. Now, once you get up there, however, you need to have the bureaucracy kind of give you the endorsement that's necessary in order to go ahead and manufacture. Now, here's the things that we found. I went back and I started looking at it. And the first thing we ended up determining is that whatever we send up there, it's got to be lightweight. So, you can send nano particles up there. You could put in polymers. You could create nano steel, as they call it, which is 100 times stronger than steel and 10 times less the weight. But it's very heavy. You're talking about bringing up huge amounts of chemicals and bringing back a huge amount of finished product that's going to end up weighing quite a bit. So we're like, that won't work. Let's go over here and look at the stuff that's very, very lightweight. And so we started looking at things at the atomic level. And you end up finding out that you can make substrates up there that are very, very pure, that you can't get here on Earth. You can do molecular structures that you can do, that you can produce up there that are very pure. In the case of tissue growth, if you have the division of a tissue and it becomes differentiated, which happens on Earth, is that you end up, as a tissue or as a cell divides, it divides by bringing over the DNA and the RNA into the accompanying cell. You don't always want that. Stem cells, as an example, you want them to be kind of partially programmed so they continue on with their life aspects of the cell, but you don't want it to start saying, hey, I'm a heart, and I'm going to start growing heart tissue. You want it to be able to put onto something and say, oh, that's my new instruction set, and they pick up the RNA from that, and they do it. You cannot make that on Earth. It won't work. Okay, you can do some of that. You can get kind of there. In fact, the Germans just a couple of months ago have heart and liver that they can make tissues from, but you can't go and just put it on anything and say, okay, I want you to go borrow the RNA, unless you cultivate the cell in space. That's really valuable. I mean, you're talking about billions of dollars of a market there. Proteins, the DNA helix that's made up, the building blocks of that, the Legos of genes are proteins. And if you go in and look at a protein at the atomic level, they're very, very complex. Is that when they wiggle the entire time, they're in action constantly, the atoms are. You need to freeze that, and you need to take a picture of that. Well, what are you going to freeze it in? You can't get absolute zero on Earth. You can't do it. And so there's always going to be some movement. But they found out that they could freeze them in crystals. But when you freeze them in crystals on Earth, the crystals are clouded, just like you look at ice. It's never pure. Sometimes it is. In fact, you look at it, but it always has fractures all the way through it. That's the same thing that crystals would be if you tried to grow them around a protein. So they took it up to space, and they said, well, maybe this will work out because you have that equal distribution of microgravity. And they take an X-ray crystallography on that. They take X-ray, and they end up having a look at it, and they go, oh, wow, this is really good stuff. Hey, NASA, let's go do a whole lot more of this stuff. And NASA's like, we're building the station. Well, we got a bunch of drug companies that want to go do this. We're building the station. We'll let you have one maybe in 2 years from now. How's that? 2 years? I mean, come on. We got to get a business model over on the back end over here with manufacturing and distribution and all kinds of stuff. Well, maybe 2 years. Maybe we can move that up. In fact, they ended up moving it back and back and back because the priority of NASA was everything you saw on that screen. It was all about building that. And it really was, it should have been. So the time really wasn't right for those type of applications up there. The time now is right. Now, finally, it's complete. They've stabilized systems. Now they're kind of looking off towards the moon and saying, we're going to go in this direction. Oh, the ISS? Yeah, whatever. Okay? And it's exactly the mentality that you want them to have, is that, they're saying, we need a use for it. We're obligated to our international partners to support that up until 2017, and now they're talking about 2020 or 2022. It's going to be up there a while, but you're also $2 billion a year just to maintain the systems on the ISS. That's really expensive. And so they need a reason to have those, have all, something up there other than we're maintaining systems. Well, how about if we're manufacturing things in space? So they've created a thing called National Labs about a year ago. And it doesn't have much, traction yet, but it's getting traction because they know that politically they need to have something up there. So I want everybody to be sending rockets up there because I'm going to be manufacturing up there. And I want other people to manufacture up there as well, and they will.